Almost all high fire ceramic glazes craze. The clay body itself is already sealed.
I can hear him.
So, and you're looking at old ceramics, you've dealt with lots of evidence of crazing.
Especially celadon wears.
The thickness of the glaze, these are not abundantly obvious in terms of crazing, perhaps because the glaze application isn't terribly thick.
And exactly crazing is the flow of glaze, or
no, as the glaze cools, it has a coefficient of expansion and contraction, and the clay body has a coefficient of expansion and contraction. So as the newly melted glaze is sitting on the surface of the piece and they're cooling, it's not unusual that the clay body shrinks differently than the glaze. And in most cases, the glaze shrinks more than the clay body, and at some point, that tension between the two releases with a crack in the glaze.
so it's the cracking and the lines of kind of the cracking look.
Right, so you see that, we introduce that intentionally in raku.
Okay,
When you see the black soot penetrating through the clay body.
okay,
So we do that on purpose. There are times when people do glazes intentionally and then they'll stain the cracks with ink. It's a decorative strategy.
oh, okay, and they stain it afterwards, or
Yeah,
it is-
afterwards.
and then
There's
they
no crack
refire
until
it,
it
and they
cools.
refire it again, or
Not with ink, but
with the ink, okay.
possibly if you wanted to use metallic oxides. The cracks tend to be very, very thin, so it's difficult to get material into the crack that has any mass to it, like
Okay, so
metallic
it needs to be,
oxides.
waterish, because I fired a piece, a vase, and I just used celadon on it. Of course, I had put some iron oxide and wiped it off. And the outside, it looks nice. You can probably barely see the crazing, but on the inside, it's just like cracked up the yin yang. I mean, thousands of big,
Right.
very visible, easy visible cracks in the inside, but it's still smooth. I mean, to
Right.
the feel.
There's another term that you may have run into called shivering.
Shiver my timbers.
And shivering is the reverse situation where the clay body is shrinking more than the glaze. And
Then it cracks?
and it typically shows up on edges, and the glaze pops off and takes a little bit of the clay body with it. So that one's more problematic.
Is there a way of knowing what the
In advance?
in advance the coefficient of the clay?
Yeah, that was my
Yeah.
next question.
Again, we're working with raw materials that
Yeah.
are variable, so
I mean, because
unless you
when we
have a lab
fuse
to-
glass, we always use the same coefficient. Whether it's
and I
96,
have not
90.
seen information to
Oh,
suggest
nothing on
that.
clay though. Okay, so it's just experiment.
To do with it too, slightly with the pads here.
Hello, Linda. Yeah, the firings can affect it. The clay body affects it. The glaze formulation affects it. There's just many, many things. The worst case scenario that I deal with is with a raw material called spodumene.
Okay, I read that.
And spodumene includes lithium compounds. And lithium behaves unlike any other ceramic material. Everything in general, when you heat it up, it expands. When it cools off, it shrinks. It's normal thermodynamics. Has to do with the behavioral energy absorbed by the material during the heating process. Lithium doesn't shrink again. It expands and then it remains expanded. So if you have a glaze with lithium in it and it expands and it doesn't contract, it can create some rather dramatic cracking in the glazes.
And so you could pop right off of the.
In some cases, yes, I've had that happen. However, it's added to clay body to make what's called flameware. And flameware is a clay, you can make a frying pan and put it on the stove and cook with it.
Bacon fryer, or a bacon press you could make, right?
Could, yeah. Anyway, so the problem, I experimented, I made flameware, and the glazes were really uninteresting on that high lithium clay body. But there are people who enjoy the idea of making things they can use on the cooktop. Okay. Got 2 minutes for any other questions?
Just was gonna ask you about alumine, or whatever, alumina.
Aluminum oxide?
No, just alumina. A-L-U-M-I-N-A.
Right. That's the name of the molecule, aluminum oxide. You've got it written right in front of you. It's the first molecule in the kaolinite,
Okay.
Al2O3.
Okay.
That was something.
Today's discussion is focused on, briefly, where does clay come from, and then what happens when we get it hot. The crust of the Earth, our home planet, gives us the illusion of having some level of stability
Until it's the past weekend with Napa.
until 3:20 a.m.
Yeah.
Sunday morning, when
Yeah,
that
exactly.
stability proved less than desirable. So out here on the outside, we've got an inner and outer core of iron and nickel, one solid, one molten, and surrounding that is a region called the mantle. And the mantle is composed of semi-soft rock at about 2,000 degrees Fahrenheit. And our source of clay is that when rock from the mantle gets to the surface, any rock from the mantle that gets to the surface is called igneous rock.
Isn't that one of the forms of the volcanic rock?
All volcanic eruptive rock is igneous.
I thought there was
Variety
I
of
thought
means.
there was
it's right there.
three forms of rock that came from
There are.
volcanics.
We have igneous rock,
Yeah.
we have sedimentary rock, which is basically the igneous rock weathers down and is
And then
transported
there
and
was
laid down
something
in
that was
sediment.
porous.
And then the last one is metamorphosed or metamorphic rock, rock that exists and is affected by heat and pressure to transform it into something new. Those are the three basic kinds of rock.
But they actually all go through, they all actually start out as igneous.
It's all come from the center, right?
And then from that you get your obsidian and your
Many, many
and
different
the
forms
things
that
that
have
come.
everything
And
to
I
do
see,
with.
you know, well, that comes out of the volcano. They kind
Right,
of
that's
it
all
comes out,
igneous.
but it forms.
Igneous is a big catch-all
okay.
title
Okay.
for all rock that comes out of the
Okay,
mantle.
I should ignore my geology class then.
Now,
This
there
is geology class.
are three fundamental ways that igneous rock gets to the surface.
Just because that was 40
The
years
first
ago.
is in a situation referred to often as a hotspot. There are approximately 35 hotspots on the planet. And the hotspot that I'm referring to here is in the middle of the Pacific Ocean. And it's what forms the Hawaiian island chain. And currently, the big island of Hawaii has been erupting, although somewhat calmly, for better part of 30 years.
It's Kilauea.
It's the Kilauea Rift Zone.
Went off in the 60s,
And the
yeah.
night that I spent there with DK, watching the lava flow
Wow.
was
That's so
pretty astonishing.
How
But,
close did you come to that?
well, when we first got to the area where the lava was flowing into the ocean, the park ranger was there. And he warning everybody, stay back from the cliff, no, don't get too close, and all that kind of park rangery security stuff. And he said, oh, 7 o'clock, I'm done.
You're on your own now. You've been told.
Well, this doesn't, so this doesn't happen all the time. This just,
Not as dramatically as this.
yeah, but it does sort of ooze.
Ooze.
Yeah.
And ooze is the right term because it just moves very gradually and slowly. and it kind of lifts up a piece and it
That's a
pooches out. And
pretty good
so when I
flow.
took a stick and I pushed into it, it had the consistency of bread dough,
Yeah.
and the temperature was 2,000 degrees.
You didn't have a stick with
Long
it
Stick
came out.
caught on fire.
Long stick.
It's just fascinating because it cools so quickly. You can see it's coming out. This is a huge lake bed that formed while we were watching, and the lake bed continued to fill up. And then this edge lifted and it began to flow out here, and you can see in the distance here, probably 30 feet, how it's cooling and turning black.
Yeah.
So it forms this crust over the top of itself, and the hot molten rock continues to flow below the crust.
So is your feet under your feet hot?
Well, we were standing on a ridge, and I looked down, and there were blue flames dancing around because the magma
rubber?
was flowing on top of grassy fields
Oh yeah.
and just turned it straight to methane.
Oh my gosh.
And so, and one night
Melt
we
your
walked down
shoes
on
off.
it, and when we got to the point where we were looking down in the cracks, and the incandescent, the glowing rock was only 12 inches below the surface. So,
That's a little too close.
so rock can get to the surface. Again, about 35 hot spots, and other ones at Yellowstone.
What about Mammoth?
Mammoth Mountain.
Yeah.
There's a fault zone on the east side of the Sierras. Magma's coming up. There have been eruptions there in the last few thousand years.
St. Helens, right?
Mount St. Helens is the most recent major eruption on the west coast. And those eruptions happen in this condition.
Yeah.
So you're probably all by now familiar with and comfortable with the term plate tectonic. This is the working hypothesis currently that explains just about every physical relief characteristic on the planet. And this is a map that could not have been made when any of us were born.
Yeah.
Didn't have the information of the topography of the ocean floor. All of that came out of classified CIA defense studies after World War II, where they had all that submarine warfare with the Germans, the Japanese, and the Americans, and they were running into mountains on the ocean bottom they didn't know existed. The dream had always been that this is one very flat plain out here, and it turns out there's a mountain range right down the middle. That mountain range represents where North America and South America, Europe and Africa used to be 280 million years ago, joined as one massive continental continent called Pangea, all Earth. 180 million years ago, South America began to split away. Later, North America. The continents have rotated. Parts of North America were on the equator for a while. Anyway, so this is pretty much a current picture, except I've had this map for probably 20 years, and New York is moving away from Barcelona at the rate of 2.5 inches a year. From the time that this map has existed, this has opened up another 8 or 9 feet. And if you understand this notion that there are all these plates, and the continents are just like islands sitting on the plates, and they're in motion, and the Atlantic Ocean is getting bigger, then it raises the question, what's happening to the Pacific?
And the Pacific
Crinkling
is,
up.
because it's so huge, is still very mysterious in a lot of ways, because it's impossible to truly map it.
So we have bits and pieces. When boats travel that carry instruments behind them very often, and the researchers get a hold of the instruments and they have that little more information about that there are huge areas where we don't even know.
Yeah. Of course, there is the Ring of Fire over there in the...
Well, yeah, this is,
yeah.
I need to get one more map which focuses
yeah,
on center
yeah.
on the area of the Pacific so that we can see this.
Ring of Fire.
Yeah.
In any case, South America is pushing over the ocean floor. The ocean floor is relatively thin, and it's composed of very dense basaltic rock, among other parts. And when the ocean floor comes up in contact with the onrushing continent, the denser ocean floor rock dives below. And when it does that, it creates a trench
Yeah.
right here, which is called the subduction trench. So if we look at the west coast of South America, what we can see is this dark line that runs the full length of the continent, and that's where the ocean floor dives deep into a trench, pulling the edge of the continent down with it to make that valley. And that tremendous amount of compression between these two pushes up a mountain range, one of the largest on the planet, the Andes. And so all of this rock is pushed by this collision because South America goes this way, the ocean floor is going this way, and the harder, denser, colder, and fairly thin ocean floor of basalt goes down. When it gets to a depth of between 50 to 60 kilometers down, a combination of the water in the rock, the seawater, and the minerals, and the heat of the mantle causes it all to remelt. And the remelted rock begins to make its way up through the crust.
And Chile has massive earthquakes.
And if it, yes,
They just had
Chile had another one last week. That
just
the
another
pattern.
7.0 on the Richter scale is Saturday.
So what's happening, you see, is this lip of the continent's getting pulled down, bent down, and then periodically it gives way and springs back up, which is exactly what happened in Japan, except there, when this lifted back up, it pushed a huge amount of ocean inland to create that tsunami. If these are bubbles of rock are called plutons, and if the pluton makes its way to the surface, there's a pressure release and a spectacular volcanic eruption is possible. And then we have two things that are different than clay making initially. We have volcanic ash, which is carried in the wind, and we have lava flow out onto the surface. And very often with the lava flow goes a violent explosion like Mount St. Helens, and a huge part of the mountain slides downhill and pushes in, and 5 to 7 miles away the forest is laid down like matchsticks. Tremendous amount of explosive power. But there are times when this rock, this molten rock, doesn't get all the way to the surface. And it begins to cool very slowly. And as it does, it forms an interesting new version of igneous rock. Very fine grain. If you got to Morro Rock and you look at the chunks that have fallen off the top and look at the surfaces, the grain of the rock doesn't have this kind of heavy crystalline structure.
How do diamonds and precious stones get involved in
High
this?
compression.
Pressure,
High compression.
high
and
pressure.
Yeah, I have not spent a lot of time. I've read, and it has to do with kimberlites, which are these things from magma flowing upward at high velocity and surrounding rock and carbon, and that'd be a good research project, and I'm not going to do it.
Okay.
The other way igneous rock can get to the surface is in these conditions where the ocean floor is spreading and molten rock continues to come in and fill that crack. There's a volcanic eruption in Iceland last week underneath a great ice sheet. And so you can imagine when hot magma comes up underneath a mile thick sheet of ice that interesting things are going on.
I know people are going on vacation to Iceland.
Well, maybe. Maybe
Oh,
not.
they have it was on Sunday morning. They have a circular road that goes around the whole island, and it's just gorgeous.
Yes, it is. Yeah.
So, whenever igneous rock finally gets to the surface, it gradually begins to break down. That's a mechanical fracturing of the rock from freeze, cold, freeze, heat, back and forth cycles. But it also becomes subject to very weak chemical breakdown because carbon dioxide mixes with water vapor and forms carbonic acid, boracic acid. And when the granite breaks down, it forms a brand new mineral.
Aluminum
With-
oxide.
We are comfortable living in the world of chem speak.
Silicon oxide.
Aluminum and oxygen, silicon and oxygen, hydrogen and oxygen.
That's kaolinite.
A geologist would call this kaolinite. A ceramic artist says, I don't like ice, I'll just call it kaolin.
Okay.
And it's composed of alumina, silica, and water. But this is not liquid water.
Are you gonna do a little diagram?
Al2O3,
Right,
alumina,
right. Silica.
SiO2, silica, and the water. And the way this particular system works is the atoms
Okay.
of aluminum line up on one side and the atoms of silicon line up on the other. And this process is still a mystery. Not only is it very hard to see because it's so fine, clay is the single smallest naturally occurring particle in nature. And clay is formed by ions of oxygen and hydrogen bonding with the alumina, silicon and aluminum atoms. There's bond. And basically, what that does is create this flat, plate-like or mica-like structure, which is the clay particle. I said these are very small, so in this kaolin advertisement from Albion, Georgia, right here we have an electron micrograph that's 25,000 times normal. And if you look at that, you'll see that the basic structure of clay particles is flat and plate-like, which has all kinds of mechanical implications for us as we work with clay. But the source of that flat plate-like structure is this arrangement of aluminum and silicon atoms bound together by those ions of hydrogen and oxygen. This water is referred to as the water of crystallization. It is not a liquid. If you take a clump of dry clay and squeeze it, there's no water coming out of it because it's in the structure.
So it's basically a bond.
It's the bonding
Those, okay.
ions of oxygen, and they just happen to add up to the same structure as water.
Okay.
Yeah, it's just those molecules. We really, yeah.
It's
Yeah.
just bond.
Now, kaolin is a primary clay. It is the primary clay. It has the following characteristics. It's chemically pure. Its particle size, albeit very, very small, is still relatively large. And based on its large particle size, it has low plasticity. Now, plasticity is an important term that we take advantage of all of us anytime we touch clay. We apply pressure, the clay deforms, we remove pressure, and the clay holds its new shape. As opposed to elasticity, which if you apply pressure, the rubber band changes shape, you remove pressure, and the rubber band goes
Or
back
like
to its original
foam.
shape.
Or like foam.
Many, many materials that bounce back after pressure is applied. The window frames right here were heated aluminum, deformed through the plastic nature of the hot aluminum, and when the pressure is removed, we still have that extruded form that was used to make the window frame. Glass is a little bit odd
Thank you.
in this character because it's technically a liquid crystal. So it doesn't. We heat it and we treat it as if it's a plastic medium, but it never really solidifies, and over time that will slump. And if you find really old windows in the frame, you can see those
Yeah,
sag lines in the
They're
glass.
bigger at the bottom.
Those are
over millennia, yes,
Yes.
the gravity causes the sag.
Yeah, I guess some of those really old churches, cathedrals that had the glass windows and stuff, they found that the glass is thicker at the bottom of the
Yeah,
pieces.
yeah.
Of
Because
course,
they're
the
hundreds of
manufacture of
years
that
old.
glass was not done so sophisticated as we do today, where they float the liquid glass on liquid hot metal.
So it doesn't.
Gravity gives them a flat. When they hand rolled those sheets of glass, probably a little bit less likely to be uniform in thickness. But independent of that, glass is still fluid. Kaolin, it'll fire white. It's pure chemically, and it's the source material for making porcelain. And porcelain has a number of characteristics which are fascinating and useful in our contemporary world. Porcelain is, in fact, an excellent electrical insulator. The only reason that these pieces are glazed is that the porcelain is not a glassy surface, and so dirt and dust will accumulate on that surface, and the electrical wire, when things
Shade.
become foggy or rainy, and there's dirt here, can create a spark and go to ground with the electric energy. So we glaze them so they can be washed periodically, and
They started with glass and then they went to porcelain.
That's right.
well,
Yes, they
the,
used to
the
be
first glass in the world was created in Egypt.
But I
Almost
mean, the
accidentally.
electrical started using the insulators out of glass.
Oh, made
Oh
of
yeah,
glass.
they have
Yes,
glass
yeah.
insulators.
Thank you, I didn't
Yeah,
follow
yeah.
that. So in my Ceramics 1 class, I always show folks the first day of class a spark plug, because
Basis is.
it is, in fact, a combination of metal and porcelain. And the porcelain starts on the inside, outside of the engine block, and goes all the way to the inside, so that this electrode comes out inside the cylinder, and then this metal part is screwed into the top of the engine block, and therefore is grounded. And then a spark can leap between the electrode,
And the
it's
diode.
called the gap,
Yeah. Gotta always gap it
have
right.
a gap the right size,
Yeah.
and that ignites the air and fuel mixture in the cylinder, and thus we have a small
Never even knew it
explosion.
was porcelain. Never even knew that. Wow.
Are they still porcelain?
Yes, oh, that's the only material that we have right now.
Even though the heads that they put them in nowadays, a lot of them are high plastic. They use a lot of plastic parts on engines now.
Well, the porcelain has the benefit, it stands up to the heat,
Yeah.
and it insulates the movement of the electrons. Now, the clay that's originally formed up here at some elevation in many cases eventually gets moved. You get rain, washes the kaolin downhill, it's tumbling down the stream, the particles are getting pulverized with all of the other rocks and gravel and sand moving with the flood water, and eventually it all comes out and settles in a low lake basin, or it goes to the ocean, one or the other. But when this water carrying clay gets to a low spot, all the sand and gravel and boulders are deposited as the velocity of the water diminishes, and eventually you have this ponding effect down at some low spot, and clay, again, particles are extremely small, will remain in suspension anytime the water is in motion. But once the water is calm, slowly the clay particles will settle, and they'll always be the last to settle. And when the water evaporates, the clay will be sitting on top of the lake bed. And then it's subject to wind and sun, and the clay begins to dry out on the surface, and it's typically sitting on a bed of moist material in the dry lake bed. And the clay begins to shrink as the water evaporates, and it begins to form a bunch of cracks in these kind of polygonal shapes. And then the surface of the clay, drying out more than the clay underneath, begins to shrink and curl upward. And anytime you find natural clay, you can observe that phenomena.
Yeah.
Yeah.
And this is what I found in the Santa Maria riverbed about 20 years ago, when a lot of clay water was released from Twitchell Reservoir in an attempt to clear out the plumbing.
Yeah, it seems
Now, can you just go and like gather that? And
I did.
then-
That's what I was going to ask.
Yeah, and
a
then,
lot together.
and then
There's a piece of it. Yeah, we didn't gather all of it.
You'd be there for a long time.
Yeah, do you have to get a permit to
well, so this thing
mine
could
the
be,
river?
like, pulverized and reconstituted, or not?
Not reconstituted as much as it's transported by water. The particles become more broken and fractured and tinier. But it also ends up being contaminated with iron oxide typically.
No, what I meant is you could pulverize it and
Oh, I could. We do.
into clay. Yeah.
Yeah, we have a glaze back here that exists nowhere else in the world that uses this clay.
So it's from here that Cuyamashino is made.
Actually, we
I
get
mean,
it
more or
at
less,
the dam.
generally.
Yeah, basically it's the
Okay,
same.
okay, wow.
Would I find clay in my backyard? Because when I was digging my big
Oh, yeah.
deep, my pond's over 5 feet deep.
Right.
And when I was digging that up, we had a section about this thick. And at first he thought it was a shelf. He was going to leave it a shelf. Oh, that's cool. And it broke off just like clay. Just right. Yeah, like a smooth break.
Right, that's correct. Right.
Yeah, so I have this tons of all this clay.
So this is unfired. This is just the raw material. When we take this and heat it in the kiln
It's brown.
at bisque temperature, so what you see in here, this mixture is with yellow iron oxide,
Never heard of yellow iron oxide.
a problematic material that's mixed with clay and but when it goes into the electric kiln and is subject to the heat of the kiln
Like a
and
brick.
more oxygen, it then is transformed into red iron oxide. And if you catch it just right, you can get animal tracks. And you probably want to look at the cat track.
So there's yellow iron oxide and red iron oxide.
And black
And
iron
black.
oxide.
Okay.
Wow, isn't that so cool?
Obviously, you can see I've never taken biology class. Or,
So the clay that has been transported from its source of origin is now redeposited, is now finer particle size. So secondary clay, as it's called, is first of all impure chemically, contaminated with other minerals. The particle sizes are now very, very small, very fine, and
Smaller particles.
smaller particles. And because of the smaller particle sizes, it ends up with higher shrinkage. That has to do with the fact that the smaller particles, when we get them wet, the water has to cover all of the surface area of the particle. And once it's wet, that water relative to large particles takes up more more volume. And therefore, when the piece dries and that water evaporates, you get more shrinkage. Therefore, potentially more cracking.
so porcelain shrinks more than others.
Porcelain is not highly plastic. Porcelain is made from primary clay, from kaolin.
Okay. Okay.
Ball clay.
So less shrink.
Laura, would you bring us 2 trays of powdered ball clay, please?
So porcelain less shrinkage is what I'm saying.
Yes.
Yes. Okay.
Relative-
Then, relative to other
Other
clays.
clays
clay
that have
bodies.
secondary clays mixed into them.
So when you're talking about particle size, you're talking about the how compact the actual clay molecules are, right?
Okay, where's my technical advertising page with the microdrill? Oh, underneath there.
Okay.
So part of it, remember, those are
These are each little particles?
each particles of clay.
Okay, so they're not consistently the
Right.
same size. Okay, that makes more sense.
Okay.
Okay, got it. I'm thinking.
They're like snowflakes. No two are alike.
Yeah. Well, that's why I'm here to learn. All right.
Okay, so we've got essentially two kinds of clay, primary and secondary. We can blend them together to achieve whatever our desired goals are for a clay body. Clay by itself is not a highly reliable material in terms of finished firing, so we'll add other ingredients, and I'll talk more about those later. But a clay body is a blend of materials that have two purposes. One, how do we form it? Second one, how do we fire it? What do we want from firing results? The basalt that comes up here in the ocean floor stays below the ocean for millions of years. But at some point, all this ocean floor ends up crunched up against the continent, and some of it gets scraped off. And if you go to Avila Beach and you walk out on the pier, and on the northwest side of the pier there's a placard that points to a bluff over on the side, and it talks about pillow basalts, which are basalts erupted under the ocean.
Yeah.
And they burp out, and then they chill and freeze, and then the pressure inside causes them to split open, and another pillow emerges. Anyway, there's a whole cliff there. Thank you, Laura.
Where would you like it?
Right here. A cliff of these pillow basalts. So the ocean floor can arrive at, thank you very much, at the surface where then it begins to chemically change and weather.
That's ball clay?
This is ball clay, dry powdered ball clay. It has essentially the same formulation as a secondary clay that a primary clay does. And what I'm going to ask each of you to do now is take a pinch of ball clay in your hand and then add enough water to turn this into a plastic mixture . And the goal of this exercise is to create a ball of clay from this mixture. And when you get the right proportions of water and clay,
It turns into a bowl.
you can end up with the ball,
Is that why they named it ball clay? Because it can.
probably. So we have water, we have clay. Please
Sorry.
If you want to come over to the side away from your notebooks, that's fine.
I'll watch everybody. Okay. No. Oh, it's this side, right?
Oh, I'm supposed to go on here.
I think.
I think they're both.
Oh, aren't they both?
Yeah, they're both ball.
Oh, they both are? All right. I thought she was supposed to bring two different kinds. Okay.
No, I think she.
Oh, this is the hard part, huh?
I won't get any on your stuff. I promise.
No,
I
that's
can't
okay.
get it to do it.
I'll let you go.
I can't get it to go around. There you got some. Ooh.
Ooh, too much.
Oh.
Well, oh, there we go.
There's a little more.
Oh,
If you end up with a crumbly mess, add a little water. If you end up with slippery, slimy coating on your hand, add some more dry clay.
You know just how much to use, don't you?
Kind of like that.
He's been doing it a while.
And when you have your ball made, I'd like you to add to my collection.
Are you going to use this for the next class?
He uses them.
Hey, I get it. I go.
Okay.
Can't seem to get it in a ball.
About good consistency.
Ooh, I got cracks in mine.
Sticks together.
That means it's two. I got cracks in mine. Oh well.
Touch dry.
Hey, you know what? I've already got it on myself, so I have to go back to my office and play on me.
Kara?
Oh, actually,
Your right elbow has I've been doing this exercise about adding water to ball clay for a while. I'm generally inclined to think that my last semester I'll put this out with whoever can guess closest to the number of balls in there.
And those are all bisque, right?
I'll have them count.
They're all different
Those are all
sizes.
bisque.
Have your grandchildren count.
All different sizes, so you can't mathematically figure.
He's gonna make jelly beans for the kids to play with.
So
That'd be dangerous.
This AL203 and 2SiO2 doesn't have the water crystallization.
Right, because of what happens when we get it hot.
So it goes from this to this.
That's right.
Perfect. Okay. Just trying to understand all
Yeah,
of
that's a
this.
full set.
Oh, this is a full. I didn't get one.
Yeah, well, I got two full sets, so I cleared one set out.
Oh,
thank you, Gabe. One set.
there you go.
Yeah, there was another set for you too, but there were three that I had.
So if you turn to page 2, you get a vertical temperature column, and 70 degrees Fahrenheit is approximately room temperature. A little warm for me, but not for everybody, and so on average. But that's the temperature pretty much at which we do our work in ceramics. The temperature for 32 degrees Fahrenheit is not terribly common here, although it happens once in a while. What is it? We call it freezing. It's technically a phase change from when liquid water changes to a solid. Solid is called ice. And this is a trick question slightly, but I'll share it with you anyway. When water, a given volume of water, goes through that phase change from liquid to solid and becomes ice, does it stay the same volume? Does it increase in volume? Does it shrink in volume?
I won't answer because I know the answer.
Water increases. Wow,
Yeah.
I've frozen many things where I put the water level too high and they'll bust open.
Yeah.
So
They'll bust
you
the
have
thing open.
you have personal experience to suggest that water increases in volume. Somebody wants to quick chill a beer or a bottle of wine, they forget about it, they discover
They'll
that
have
liquid
beer all
expansion.
over the place.
blows the aluminum bottom out now.
Set the timer.
So we all conclude comfortably that water increases in volume. So Linda, who's now become so enthused about ceramics that she's about to retire and become a full-time ceramic artist, also is going to move to Helena, Montana in the process. And unlike the Santa Maria Valley, Helena and many other areas like that have very severe winters.
Yeah.
And somehow some magic happened in the process when she retired, but her husband took over the kitchen and now is responsible for preparing all meals.
Boy, well, don't you wish.
This is
So-
becoming more of a fantasy every minute.
So she's in her studio. She's been working all day. She has 7 cats going. They're not finished, but they're partly there. And the intercom rings, and her husband says, "Hi, sweetheart, dinner's ready." And she clicks off the light, and she heads up to the house, and they share a bottle of wine, and they have a wonderful calm meal, and she gets tired and goes to sleep. And in the morning, she goes back out to her studio, and everything looks to be just like it was when she went to bed, except that there's ice in the water bucket. She stokes up the wood stove. She begins to heat up the studio. Water begins to warm up and melt. And she looks up, and every one of the cats has collapsed. The water in the wet clay has frozen and expanded slightly and pushed the clay particles apart.
Cracked it all over.
And when the ice in the cats thawed, turned back to water,
So in Montana,
You
what
better
do
put an all-night heater.
well, you
in
have
the
to be
studio.
very careful about how you control your studio.
You don't have
You leave the heat on at night. You don't let it freeze in your studio.
And on a first-hand experience, I took a group of faculty and staff colleagues on an event called Clay Camp in January one year. And we drove and we camped up in the Los Padres National Forest, up on the slopes of Mount Pinus, and it was pretty obvious it was going to freeze that night. So we had gathered clay, we processed it, everybody made small pots. Knowing it was going to freeze, we built up the fire, and we put the pots not in the fire, but around the outside of it. Woke up in the morning, everything was fine, the fire still had some warm embers. Then the sun came up, and the side of the pots toward the fire were fine, and the side of the pots away from the fire went.
So it needed to be turned on a regular basis.
Yeah,
Or put a
nobody
rim
stayed up to
around
do
the
that.
thing and that reflected the heat back on them.
Yeah, there were many things we could have done.
Yeah.
Didn't we? I remember we had a student one time, long time ago, made a bunch of hands, and they were bisque, and then she froze
She
them.
raku fired them.
She raku fired them, and then she put them all in the freezer. And then when she brought them out, she displayed them. As it got warmer, they started kind of exploding, and then when they were melting, they just kind of.
Why did she freeze them? Was this an experiment?
It was
Okay,
a demonstration.
So Dana's art project, an installation art
That's right,
project,
Dana. Yeah.
and she encapsulated each of these slightly smaller than life-size hands, and raku fired them. But raku firing doesn't make the
Slow
clay non-porous. So some of the water before it solidified was inside the hands, and so it caused some fracturing of the pieces. But since they were all in a big globe of ice, it wasn't until the ice melted that fingers fell off and a few other things.
Yeah, I remember that. That was very interesting. Very.
Okay, 212 on this temperature column represents another phase change. We usually call that boiling, but we're going from a liquid to a gas.
So it's vaporous?
Well, steam, I mean, but quite technically, it's
Liquid
water
vapor.
to gas, liquid to gas.
You have to forgive me. I keep throwing in some of my physics terms every now and again. So this is the same stuff that
You're engaged.
that I teach.
Now, same question. When water, a given volume of water changes to steam, does it get smaller, stay the same volume, or expand?
Well, it expands because the molecules are.
Yeah, but it's dissipating out of the form.
No, if you were to capture it as it
it's
did,
much
it would
more
push the sides of a
energetic.
balloon out,
I would say it's energetic. It's expanding because if you try to boil something,
like what makes a
contain
hot
it,
air
It's
balloon blow
expanding
up.
like it's expanding.
It
Yeah.
expands. So
just like when it does when it
If it's in
freezes.
a-
But as it
If
expands,
it's
your
in a
whatever it's in
container,
is
it will
shrinking.
try to, it will create, it will, and it can't expand. It
will like a bomb.
increase the pressure inside
Right.
the container. 'Cause it will push out.
but it won't expand. Oh, okay.
Any of you ever had a tea kettle
Yeah.
that had a whistle device on the spout?
Yeah.
I'm really grateful for that because I'll put my water on and
Forget
go
it.
off to the computer and I hear it beckoning me back for my tea.
Except when you can't hear it anymore.
What makes this whistle operation happen?
The air expansion inside.
In
You're
this case,
creating, you're blowing in and creating a pressure, and it has to escape,
Yeah.
and it makes the noises that escapes through certain vents.
I think that's a fair description.
yeah, the holes constrict the.
So, in that tea kettle, we have pretty good evidence of the fact that what we started with water, now there's enough pressure inside the container to cause the pressure to try to escape. It goes through the whistle device. Bob goes away from his computer and makes tea.
Okay.
Any idea by what factor water expands as it turns to steam?
10 times?
I don't know.
No, it has to do with heat transference.
I had to go to DK, chemistry
Yeah.
guy on this
yeah.
one.
This is,
And what he came back and told me was that the expansion is by a factor of 10,000 times in volume.
Whoa.
yeah, I was going to say, it's got to be exponential, but I don't know really what the factor is.
So,
Did you ask him how much the expansion of when it crystallizes, as in ice, how much it
no,
expands there?
no, that because
It's
that's visible. We can see that and measure it, and it's relatively small.
Okay.
Yeah,
Now, the
it's fairly
trick
small.
question part of the water expanding when it turns to ice is actually it's not true.
Yeah.
The H2O, hydrogen, oxygen, oxygen. So the molecule, which is water, has that sort of configuration.
Right.
As part of how it fits together and maintains a liquid. At 2 degrees above freezing, this configuration changes, and that's when the volume increase happens, actually before it freezes. But in an ice cube tray, where it's freezing from the outside toward the center, gradually that expansion is forced inward and eventually upward on that ice cube.
And it also doesn't continue. There's a very definite at 4 degrees C I forget what it is in Fahrenheit,
Yep.
but it's a very definite
One time only.
minimum density, maximum expansion, and after that it goes back to behaving fairly normally. And you keep freezing it to colder temperatures, it starts to shrink again. So.
So, we're concerned about this vast expansion from water to gas if the water's still in our clay. It doesn't take long before that pressure exceeds the strength of the clay holding together. And that can cause a steam explosion and ruin your work and sometimes ruin the work of your neighbors. So we treat work with a lot of respect. We waste a lot of energy making sure things get dry rather than waste a lot of work. Place a line about halfway between 212 and 1000 and label it 600 degrees Fahrenheit. We'll skip it right now. And then the next one up is at 1000 degrees Fahrenheit is the temperature at which incandescence begins.
Oh, it starts to glow?
Incandescence. And you know immediately of an incandescent light bulb?
Yeah, so it starts to glow.
The molecules of the material are beginning to vibrate so fast they give off visible energy.
Okay.
And incandescence is the term for that visible energy. And you'll have a handout later in the packet that looks at color and temperature, where you can actually guesstimate the temperature inside the kiln based on the color of the light coming from the kiln.
Yeah, that's true on the light, because my husband used to work with a 30,000 ton kiln, or kiln, not kiln, but a rotor tree, he used to put all kinds of metals and stuff in it. He worked at a lead refinery, a lead smelter. And he could look, from all the years experience of the 18 years experience he had there, he could open up a thing, and just by seeing the color in there, he knew what temperature it was.
It comes from
Orange or yellow or
experience. Yep.
whatever.
Yeah.
And I've had 2 occasions where I had to evaluate shutting off the high fire kiln based on color. When we lost the cones, and then I said, "That looks right."
Yeah, you gotta have the knowledge, yeah.
He can come in handy with the.
He won't even let me fire it.
No. We'll get there.
In between 1000 and 1200, you can make another line at 1100 degrees Fahrenheit. Now we can go back to the 600 to 1100 area. We'll talk about this again on the next page. But this is where the fundamental change happens, where clay changes from its original chemical formulation to a new one, in which the water of crystallization is driven out of the matrix, and we end up with an aluminous silicate, which you could also simply refer to as ceramic. And if we take material, if we take clay that's been fired up to that 1100 degree temperature range, pulverize it, grind it into a fine powder, mix it with water, nothing happens. It's not clay anymore.
Repeat that.
Yeah, please. All right, so from 600 to 1100 degrees, the clay changes from the original chemical formula to a new one. And then the water crystallization leaves. And then what
Well,
happens?
what you have is ceramic.
Okay.
Something that's going to be around for thousands of years.
Okay, so when we're talking about ancient civilizations that did firing in the earth, would that be the 600 to 1100 Fahrenheit degrees that they would go to, or?
Hold that question for just a moment, if
Because
you
it'll
will.
never go back to regular clay again.
Right.
That's correct. We've made a fundamental chemical change in the material.
Never to return.
If you look a little higher up there
Yeah, can't
at
grind it.
1450 Fahrenheit, that's the temperature of a wood fire in calm conditions. And when I first read that, I thought, well, really?
We talking embers or?
Just,
Oh, when it's just a
like
little
when you're looking,
teeny-
you're at the beach and you're having a campfire and you're staring into those glowing coals.
Because the more wind creates more oxygen being fed into it, which would drive the fire higher.
That's correct. So, under calm conditions,
Oh,
that orange
calm
glow that you
weather,
see
calm
is
conditions.
1450. So I took a high temperature thermometer, we called it
Pyrometer.
thermocouple,
Oh,
shoved it into that, did it in multiple tests, multiple fires, 1450 degrees. So I think that gets at your question, because almost all the pottery ever fired, perhaps 90%, well, I don't know, maybe that's 80% now, was fired no higher than that wood fire.
Okay, so that's good. Thank you.
I think that's the part that you find amazing, because you think a wood fire can't possibly be as hot as what we have in the kilns there, but it's in fact hotter.
Potentially. Most of the kiln firings that we do are higher than the wood fire. You can draw a line all the way across the page between 2000 and 2100.
Cricket line.
That is the line that differentiates a couple of things, but the most important is below that line, everything is referred to as earthenware. E-N-ware, earthenware. E-A-R-T-H-E-N. And the characteristic of earthenware is that when it's fired to maturity, the clay body, or now ceramic body, remains porous and absorbent. Above that line, we begin to deal with the phenomena of vitrification, which means to become glass-like. And so above that line is the range of stoneware and porcelain.
Now I understand more of the earthenware. Stoneware and earthenware is not vitrified.
well, earth, yeah, you think of
Earthenware
dirt,
is not
and
vitrified.
Stone, you think of something
But
very
is stoneware?
hard.
Stoneware is vitrified, but
Vitrified.
stone. All right, so when we're bisquing, when we do the bisque, we're in the earthenware stage
Correct.
with high fire clay.
Correct.
Okay, and then once we glaze it, we put it back in, then it becomes vitrified completely, and become
Nearly so.
okay.
So that high fire stoneware clay bodies, porcelain clay bodies, once they're fired to maturity, will hold water without glaze.
Okay.
So we take advantage of the fact, as I will right now, with this is low fire white clay body, and it's very thin walled. In a relatively short period of time, water will actually migrate through, and we'll be able to see it emerging on the
I
outside
can
of
see it
this
emerging.
Where?
Right
Darkness?
there. Yeah,
Yeah, I saw that line get darker right there.
right there, and then up.
And not the black fingerprints, but that looked a little.
So
Well, how much water did he
this
put in there?
ceramic,
Oh, I see it on
it's
the
only
inside.
about this high. This ceramic material, which has been disc fired, has what are called interstitial spaces, spaces between the clay particles. The clay particles themselves are randomly oriented. Again, they're really tiny, and the spaces are all really tiny. But the spaces between the particles are large enough that the water molecules can penetrate and move through them.
Okay, now I see it. That was dirt before
Yeah.
that. I can see the wetness now.
Yeah, right there.
Yeah, yeah,
You
yeah.
can definitely see that
See right
dark,
here?
Yeah.
darkness
Oh,
there.
okay.
Definitely.
Oh, yeah.
Yeah.
Oh, you really see on that side.
Yeah.
So don't
We're
think bases.
in high fire work, we're taking advantage of this characteristic. We want the ceramic forms, after we have bisque fired them, to still be porous and absorbent. Because when we take the bisqueware and dip it into a bucket of glaze, the water in which the glaze materials are suspended penetrates into the ceramic bisqueware and leaves behind a residue of the glaze making material. You'll notice to the right-hand side of the vertical column on page 2 are a series of black triangles. Those black triangles are a symbol for pyrometric cone. Pyro, fire, metric, measure, pyrometric cone. So whenever you see somebody in the literature, it says cone 10. We're talking about a pyrometric cone. And one of the characteristics of what we do when we apply heat to our work is we change the material chemically and physically as per the switch from clay to ceramic, or when we're using glazes, or when we're using iron oxide as a colorant. All these things are changes that are taking place during the firing, and we choose materials specific to temperature, but we're not any longer concerned with the numeric form of temperature, because now we're concerned about the work-heat relationship between the materials and being hot long enough. Now, you know something about this if you've ever baked a cake, and you need to leave the house in half an hour, and you're supposed to bake the cake for 45 minutes at 325, and so you crank it up to 375 and leave in half an hour, and when you slice the cake, the inside is a gooey mess, right? Because the heat has, the heat,
You can't make it cook faster, huh?
Nowadays, you stick it in the microwave and it cooks it.
It worked with the meat.
it takes time for the heat to penetrate through the walls and the thickness of the material that we're working with. We can fire thick stuff.
Yeah.
But the kiln that I got this brick from fired for 2 weeks.
Slow.
And a way they knew that the kiln had reached temperature is they walked up on top of it. It was a stack of 1.5 million bricks with 2 layers of fired brick around the outside for insulation. And when they reached maturity, the top of the stack began to sag.
That's the only way they know it's done?
Yeah,
Oh my gosh. Wow.
it's pretty cool. It'd go over there in the middle of the night.
Because they've all shrunk and cooked.
Yeah.
However, if the brick gets too hot, particularly this kind of material, it's contaminated with iron and other minerals. It can be subject to heat, and if it gets too hot, the brick can then turn to glass and begin to melt. This one was in the firebox where the gas was blown in, and as you can see, it's been distorted. Gravity is not your friend every day, most days.
Gravity and high heat, you know.
That's incredible.
Interesting, yeah.
Wow.
It is, that's really, actually really neat, isn't it?
That's extraordinary.
As you drive around San Luis Obispo and look at people's yard fences, it's not unusual that you will see big, they call them clinkers, but they're big chunks of brick that are all fused together. And so they, when they take the brick kiln down, this last stuff they jackhammer it apart, and people, over the years, the brickyard is now closed, but people would gather these up and use them as ornaments in their yard fences.
Because they're probably melted in all
Yeah.
different shapes and
Oh, yeah.
everything else like that.
It adds a little bit of
Yeah.
character to it.
Yeah, not necessarily recognized immediately by folks who don't know about the brickyard, but certainly gets this ceramic artist excited.
Yeah, I mean, but it's just,
Yeah.
wow.
It almost reminds me of volcanic rock or
Sure.
yeah,
Molten rock. Yeah.
that's incredible.
Get out there on the Highway
No, I
395.
see.
So, you need to know about pyrometric cones. And for that, I'm going to jump you ahead right now to page
5.
7.
my version of it doesn't have the number on it, but it's page 7 on
Okay,
your
page
handout.
7.
And there are a couple of things I want you to look at this chart a little bit and see if we can. First of all, the list of pyrometric cones starts at cone 022 on the left-hand side of the page and goes all the way to cone 10. In reality, the pyrometric cones go from 022 all the way up to cone 42.
The cone what?
42.
42.
But that's for the ceramics industry to make pure aluminum oxide bits for turning stainless steel, and it's way out of our range. The range that you see here is pretty much the ceramic artist range. Some people go up to cone 11 or cone 12 perhaps, but this is our target range. Now, turn back, hold on to 7, keep that page open, but turn back to that page 2, and you'll notice that the pyrometric cones that I indicated there start at 020 and go 018, 016, so as the temperature's going up, the numerical label is appearing to diminish. But at the earthenware, stoneware boundary, you lose the zeros, and now you go with whole integers from 1 upward.
No, it just reminds me of mathematics and the integers that were on the one side.
Reminds me of
the
cable sizes, how they go.
Okay.
Learned that.
Yeah, screen sizes,
Yeah.
canvas sizes, just
Yeah.
lots of variations on how people have counted threads and such.
Yeah, they call it gauge instead of cone. And
Okay,
Yeah.
so you see the reference now that we've turned it upside down. Now, where the word cone is on page 7,
Yeah.
look across. You'll see 27 Fahrenheit, 15 Celsius, 108 Fahrenheit, 60 Celsius, 270 Fahrenheit, 150 Celsius.
Yeah.
The top of those columns, right opposite the word cone.
Yeah.
Yeah.
What those are telling us is that the pyrometric cones, which do this to indicate the accumulation of work heat, the end point temperature at which a cone softens and bends over is dependent on how rapidly the kiln was heated. So, for instance, look at cone 010 and look straight across and look at the end point temperature in Fahrenheit. At 27 degrees per hour, the end point temperature is 1636. At 108 degrees per hour, the end point temperature is 1657. At 270 degrees per hour, the end point temperature is going to be 1679. So fortunately, we don't have to sit there with a grid and try and figure out how fast we've been heating the kiln. We just trust the pyrometric cone is going to bend over at the appropriate time, and when it does, we know it's time to shut off the kiln. The new electronic computer-controlled kilns sample time and temperature continuously during the firing, and they have software that shows what that curve to arrive at the work heat is. In the past, we always used to have mechanical pyrometric cones in there, and then when they softened and melted, the lever arm would drop down and the switch would shut off.
That's what I have.
Just a quick question on cones. When they make, say, a cone 10, you don't have 3 cone 10s because they'd all lay at the same time.
Right.
So you have to kind of figure out your mid-range, what temperature and what cone that
So,
you would do.
so if you look at the edge of this one, you're going to see it's 8, 9, 10.
Okay.
Okay, it's time for a 10-minute break for whatever you need a 10-minute break for.
I see it.
I'd like each of you right now to look for cone 6, not 06.
Cone 6.
What would be the endpoint temperature for cone 6 at 270 degrees per hour?
2269.
2269, yeah.
I can't even hardly see that.
Me neither. Cone 10.
And 2381.
2381.
Oh, I know what I was going to ask.
Oh, it's not a whole lot of difference between. There's not a whole lot of difference between cone 6 and cone 10, is there? In temperature. In temperature.
Well, that's on that speed.
2269 versus 2381. That's
Yeah, but you'd
only.
be surprised how much 100 degrees makes. It makes a big difference in glass, so I presume it makes a big difference in clay.
It's always about time and temperature.
Yeah.
So if it was 2381 for a short period of time, maybe not so much. If it was for 3 hours,
Yeah.
big difference. This device is called a thermocouple, and it's 2 different kinds of metal welded together at the tip. And when that tip gets hot, it generates an electric current. And that electric current can be measured on a couple of different devices. An analog device is one that's got a pin that moves, or in the case of the device we use now, a software-driven digital readout. Now this was in the kiln, so it's showing a temperature a little bit higher than room temperature right now, but it's cooling off. But if I
It's at 90. Oh, he's heating it up. Wow. Oh, yeah. Don't burn yourself. Wow, really, it goes up fast. Mm-hmm. For your camera.
Oh.
Made it to 400 and something.
400.
And now it's dropping.
Yeah. Fancy.
So we use this device
I gotta
set
use
up
the dial
in the
for
kiln, not to tell us when to shut off the kiln, but to be able to watch the increase or decrease in temperature during the firing. Because several hundred degrees isn't necessarily going to be really obvious to us by eye and color. So by using a thermocouple in the kiln, we can keep some level of reasonable control over gaining heat during the firing process. This is a book of the last couple of years of firing logs for the high fire updraft and downdraft kiln. Recent firings were in the updraft kiln. So last week the endpoint temperature was 2321. The week before 2291. Back in May 2310, 2294, 2288, 2305, and all of these were for a cone 10 firing. So I'm just wanting you to understand that the temperature as measured in degrees Fahrenheit or Celsius is not terribly relevant to us. It's what happens with the pyrometric cone when it bends over.
This is just a helpful
It's,
to start
well,
really watching.
There are many, as you'll see here, there are records in there of many different times during the firing. And as, particularly with the updraft kiln, as it gets hotter, it tends to go up and plateau, and it will hold. So then I have to let a little more oxygen in to get more heat out of the fuel, and the temperature will climb again, then it will plateau. And so it goes through this stair-step process and being able to gauge that. And we get to a certain point around 2200, and then the cones begin to soften, and at that point, then the rest of the firing is, I keep the numbers, but this is really what I'm watching, waiting
How
for the
often
cone.
does one check? Put it in the book.
More often later in the fire.
More in the, yeah, more in the.
As we get toward the conclusion of the firing,
Oh, okay.
maybe every 15 minutes.
Really?
Early in the firing, maybe once an hour.
Okay.
Yeah.
So
once
if you
a
want,
half
so
hour.
if you wanted to keep a chart like that, we would have a chart that would say temperature, time, temperature, and then, what else, and then just write notes about it? Oh, thank you. Temperature, and then
On temp.
cone
kinda
F
what you're
hour,
looking
no, what's
Fahrenheit
cone F
an
hour?
hour.
The delta, the triangle,
Yeah,
That's the cone.
yeah,
the
the
cone.
cone F hour, but you put the time and the temperature.
that's not cone in this case though.
No, it wouldn't.
Sorry. In this case, delta F per hour is a calculation for how rapidly it's gaining heat.
And how do you calculate that?
I'll show you right now.
That's that one thing in there. Says, okay.
By the way, stepping back to earlier,
Okay,
Yeah.
we added liquid water to dry clay. That's called the water of plasticity.
Okay.
okay.
Every clay body has, when we're working with it, has 20 to 25% by weight is water. Water of plasticity. As you know very well, when the clay dries out, it's no longer plastic. And so 212 degrees is the critical temperature for the water of plasticity, because that's the point at which the water turns to steam. If it's still in the clay body, it can create a series of breakage problems. Okay, this is a theoretical set of measurements during a firing. So at 2 o'clock, temperature is 2015 degrees. At 2:30, it was 2035 degrees. And what I do then is I take the difference in temperature, which is 20 degrees F. I haven't done this for a while, so let me think it through here. And the time is 30 minutes, which I break into 5-minute increments.
So it's 4-degree increment increase each time.
How many 5-degree increments are there in an hour?
30? No, 5? Oh, that makes it more than
5-degree increments.
60.
12.
Oh, shit, I can't even, oh, God. I got you all confused, didn't I?
I'm confused by what he wrote up there when he was talking about.
Count on my fingers.
My mind's not working. Gosh.
Okay, so in an hour, so what I want to know in this column is how many, during this time period, although it's a half an hour, what's the rate at which the kiln is heating up in a per hour basis? So I divide this by 12 times 5.
They always complain about, what do I need math for in my life? Everything.
So 20, turn it on, that always helps. 20 degrees divided by 12 5-minute increments in an hour. And that's not right. 20, well, not multiply, divided by 12 times 5 tells me, it doesn't look right either.
You wrote multiplied by up there.
There we go.
It's supposed to be
10
divided.
over 6 times 5.
Actually, you could even be 5 over 3.
That's right.
So what does it come up to?
Well, it's showing me it's 8 1/3. And that can't be right because it's only gone up 20 in a half an hour. What am I doing wrong? I stopped doing this a long time ago, but I wanted to share it with you.
As you got all these other people doing the firing now.
No, we got
Well,
a
it
track
should be-
record.
If you're looking at the change in degrees per hour, and
Yeah.
it changed,
In a half an hour.
it changed 20 degrees in a half an hour, it should
Just
change
40.
40 degrees.
Well,
in a-
if it's constant.
I see, oh.
But it isn't- it
okay,
isn't
all right,
con- you
all
can't
right.
rely
So
on it
we're-
being constant.
So we're basically looking at little increments, we're basically doing calculus by hand here.
Yeah.
That's why I don't.
Never took calculus.
Yeah,
Maybe if I take 20, this is it. It was 5.
5. Yeah.
It's just 4 degrees a minute.
5
Yeah, it's
minutes,
4
30
degrees a
minutes
minute.
is 6. 20 divided by 6 times 12. That's it.
Excuse me, Bob. Goodbye.
Unused information. It takes
All right.
forever, right?
20.
20
Over
divided by 6 times 12. Okay. So in this 30-minute increment, we are gaining heat at the rate, but that's a half an hour.
No, that's still getting you.
Well, that's right, this is 20 and now we're at 40. Okay.
Yeah, because that's
Yeah,
at
we're
per
still at
hour,
40.
so,
Okay, so
yeah, it's still 40.
20 degrees divided by 6 5-minute increments times the fact that there are 12 5-minute increments in an hour. And so for this block of time, we're going up at the rate of 39.9 degrees per hour, even though it's not an hour. So I come in at 2:15, and I look at this, and it's now 2:55.
Now it's gone up another 20 degrees.
So I've gone up 20 degrees in
Wait a minute. You.
3,
5-minute increment.
whoops, 45.
Thank you.
Now we're going backwards in time. This is really getting very
The time
existential.
machine.
My fuzzy math is bad enough. You're not helping me.
So in 15 minutes, we've gained another 20 degrees.
Right.
So that's 4 times 20 is 80, so that's 80 degrees an hour.
20 degrees over 3 times 12.
20 divided.
So you're going down to 3 because it's only 3 5-minute things. Okay, got it. Now I get it.
And now, this indicates that
See?
for this 15-minute block of time, we were going up at the rate of 79.9 degrees per hour. The target, in general, is 100 degrees per hour.
But
So
now,
if you suddenly find that you're going up at 200 degrees per hour, you're firing the kiln really fast. Mary Ellen, you're looking perplexed.
well, no, because I don't consider, I know what the 1.1 difference makes, but I mean, the way I did the math, it comes out 40 and 80.
Yeah.
So, I mean, without
Well, I
all
just-
this fancy math,
No, it's just calculated.
I know,
math. It's just-
so still, but I
could
did it without
round
this
it off.
times and divided and all that stuff.
if you can comfortably do that in your head, I'm choosing some very obvious number combinations to
I do
simplify
mine with
it.
the calculator, so there's no fuzzy math involved.
So that you
So
asked
then what's the purpose of that? That's telling you how much faster
if my
it's going up?
target is to be going up at the rate of 100 degrees per hour,
Right.
and I'm well below that, then I
Right.
need to modify the firing to increase the heat gain.
And how would you do that? By adding oxygen?
I can add fuel and I can add oxygen. Those are the two variables.
Okay.
Fuel being the gas and oxygen being oxygen.
So anything over 100 degrees of climb
Per hour.
per hour, anything over that can risk some problems, cracking.
Most of what we do in the high fire process requires time for glazes to melt, off gas, smooth over, and give us a nice clean surface.
And you found that going 100 degrees per hour
Is this a-
gets you that?
That would be a maximum. yeah.
Okay. Oh, maximum.
That'd be a quick fire.
And the longer the firing,
Yeah.
oftentimes the higher the quality of the glaze surfaces. The longer the firing, the more we're spending on fuel. So it's a balancing act. When I first arrived here, I wanted to find out how fast that updraft kiln could get to cone 10. 3 hours.
Wow.
3 hours for 2,300 degrees?
That's amazing.
Stuff that was in there wasn't worth keeping, but I found out what the kiln's potential was.
Is the reason it wasn't worth keeping because it takes the moisture out too fast?
No,
or
those pieces
it's-
are misfired. No, the glazes
Okay.
weren't smooth. They were
Oh.
crusty and pieces cracked and all kinds
Just,
of
yeah.
technical problems.
So the reason why you're going up slowly is because of the silica and all the way it's smoothing.
All those materials have to blend together.
Yeah, you're cooking together. They're
And
cooking.
it takes time and heat to get that done.
And they,
Has
and
to
they
be
each of them
savoring
absorb
stuff.
heat at a different rate. So if you're cranking the heat up, some of them are gonna heat much faster than other parts of
That's
them.
an excellent point. Yeah.
Position in the kiln probably makes
Whereas if you do it slowly, those differences are minimized.
So the key point in this discussion is that we use pyrometric cones to know when to shut off the kiln because they are the best evidence for the work heat having been accomplished. Okay, back to page 3.
Effects of heat continues.
What a mess. Oh,
This
we'll
is a
just-
repeat of the temperature column, but now with some dashes and some lines and stuff. So starting at the bottom,
70.
in 72, 212, what we're dealing with is drying the work. Moving the water of plasticity out of the clay. And why are we concerned about getting the water of plasticity out of the clay?
Because of shrinkage.
Well, we
Tell
wanna
me-
solidify it.
Tell me what you mean with your discussion of shrinkage.
Well, you don't want it to shrink too fast, and you want a consistent off, getting rid of the water.
Okay, so in most cases, the shrinkage has been completed whenever the clay body changes from dark color to light color. At that point, the clay particles are now resting against each other. There's not going to be any more shrinkage, even though there's still water in the interstitial spaces. The shrinkage is done before the pieces get to the kiln.
Okay.
And I realize the 70 to 212 suggests that whole plasticity phase, and that's where we do need to think about that before pieces dry too quickly. But in terms of the firing process, in that range, we're just drying them out, making sure that they're ready to go above 212. There's a dashed line from 400 to about 1,000. Let's ignore that for a moment. And we're going to go to the dotted line. And at least when I made this version of the chart, I gave you a different number earlier. That is the ceramic change.
800 to
800 to 1325. Earlier today we talked about it from 600 to 1325. I think the main thing to keep in mind is there's a temperature range where we are chemically changing the nature of the material from clay to an aluminous silicate ceramic material. We talked about grinding it into a powder. It's never clay again. There's a curve bracket that runs above 1,000 to above 1450. This is a period of time referred to as sintering with an S, S-I-N-T-E-R, sintering.
S-I-N?
S-I-N-T-E-R-I-N-G, sintering. And now what's happening is that the clay particles, once we've gone through the ceramic change, the clay particles are active. They're incandescent in color. There's a lot of vibration going on. And where the clay particles touch each other, there's friction between them. And that friction begins to partially melt them at the point of contact. And sintering strengthens our bisque ware. If you take clay that's only been fired to a lower temperature, just above the ceramic change, you can carve it with an X-Acto knife. It's not clay anymore, it's ceramic. So sintering gives our bisque ware additional strength. And then the rectangular bracket up above, you might top that off at 2300 versus 2400 at the very top. Is the range where we're dealing with vitrification to become glass-like. And you'll notice none of these happen in, you don't arrive at a temperature and say you're done. These are bracketed time periods and heat periods where the changes that are taking place happen gradually. That's the benefit of a slower firing. Now, with a studio that has 50 or more beginning ceramic students every semester, in the 2 Ceramics 1 classes, getting pieces dry and making sure they're safe so that we don't blow them up and cause everybody a great degree of frustration, we set up the electric kiln to go up in temperature to 180 degrees Fahrenheit and hold at that temperature for 10 hours for our initial bisque firing. When people make big cats or pigs or such, we don't even use the electric kiln, we use a gas kiln, and we'll warm them, keeping it below 212 degrees for as much as 24, 36 hours.
That's to keep it because it's so thick.
And when you heat things, they expand. If you take a really big piece and you heat it,
It expands more.
it expands unevenly and quickly in some areas and not in others. It creates a lot of stress, and the stress can lead to cracks. So the purpose of these brackets is just to call to your attention that there are these phases that take place during the firing process that we need to respect, and a little bit about why we're doing them. Now, if we can go back to that dashed line from above 1,000 down to 400. And if you look at page 8 in your handouts.
Can I ask you something about sintering? I wrote down the particles are active, they become incandescent, and then I have here where I said it begins to melt, but that doesn't seem quite right. Is it because
at the point of contact. So if you look at that that sequence of sketches on the upper right, start on the top one and draw a circle around each of the clay particles in that top diagram. And that indication is wet clay, where you have water, a membrane of water, wrapping around each of the particles. The middle sketch is once the clay is dry and the water has evaporated. So the shrinkage that's taking place is most evident in this from wet-looking clay to clay that's changed color. When it's changed color, it's still damp, but it's not shrinking anymore. Sintering then is indicated on the bottom of those three, in which the particles, where they touch each other, are causing enough friction to partially melt and strengthen the connection between them.
Yes, okay, good. That's what I was missing. I was looking at that and said, I must have misheard him, but there I just didn't have the rest of it.
Thank you. Okay, I'm looking for page 8, so I'm going to go back over here.
Page 8?
Page 8 is all these.
Forms of silica and crystal changes.
Plus a bunch of
So-
algebra.
You can ignore the bottom two panels. They're there if they're of any use to you. Sometimes people are more comfortable talking about degrees centigrade versus degrees Fahrenheit. And so there are a couple of, there's the way to calculate it and the way to look at the chart. However, we're looking now at the top, table 21, forms of silica and crystal change. I've mentioned to you that things expand when they get warm, and things shrink as they cool, except for lithium compounds. So on the left at the top, it's the alpha-beta cristobalite change at about 250 centigrade or 482 Fahrenheit. What it happens as the piece heats up, the crystalline structure changes in orientation, and it yields an almost instantaneous 3% expansion
Wow,
in physical size,
that's big.
or during the cooling phase, a 3% contraction. 573 or 1053 Fahrenheit is a 1.5% expansion or contraction. The third of those, at 1598 Fahrenheit, the quartz dicastrobalite, one of the interesting characteristics of materials when they are incandescent is they can withstand a great deal of shock, thermal shock and size change. They're nearly fluid plastic because of the incandescence, the vibrations. So we really don't have a concern about this problem at the lower, or excuse me, the lower on the chart, but the higher temperature. Our concerns are at 1053 and 482. If you will, Vi's been telling me about the grand dream of the super platter.
It's a big platter.
And this piece is sitting on a kiln shelf. And the kiln shelf's on post. And we're slowly heating the kiln. And these flames are licking up the edge of her piece.
Oops.
It doesn't take a lot of thought process to realize that the edge of this super platter is going to heat up faster than the center of the super platter, which is sitting on a cold kiln shelf and hasn't really warmed up yet. So during the initial phase of the firing, we have to go somewhat slowly through that 482 degree Fahrenheit transition, or this edge is going to suddenly expand by 3%, while the center is not yet there and not yet changing. So the heating up cycle, we need to be very respectful of that and heat up slow enough that we're not causing that kind of stress and the related cracking that can go with it.
So when we're talking about going, when you're warming it up to the 482 and then it's got a 3% sudden expansion, and so it almost sounds like as you're heating this thing up, that it's it's letting go of certain properties, and then you heat it up, and then it lets a little bit more out, and then does that make
Yeah, I'm not quite sure what you're describing as getting let out. Well, water vapor
Water.
below 212,
right?
but at this point we're well above that.
Okay, so well, when you're talking about the sudden expansion,
Right, it's within the crystals of clay. Now, there is no alpha or beta cristobalite until the piece has been bisque fired once.
okay,
And then each subsequent firing, more of those crystals develop in the matrix of the ceramic material.
all right.
But when we cool down, we've turned off the kiln.
The edges are going to cool.
There are burner ports down here that are going to let cold air into the kiln. And that cool air,
It's going to hit those things.
because there's hot air in the kiln exhausting out the top, now we have cold air rushing in here. This is a hot kiln shelf. The piece is hot in contact with the kiln shelf in this region.
Yeah.
Pardon me for just a moment. I'm going to go get a demonstration piece. I'll be right back.
You can just imagine what.
Check with me afterward. So here's what happened to a piece made of B-mix that was fired in the electric kiln.
That's gorgeous.
Bisque fired. The electric kilns are notorious for cooling very quickly.
Oh. Wow. So if it had been in the gas kiln, it wouldn't have.
Anything like this of mine is only bisque fired in the gas kiln now.
Yeah.
I don't blame you.
Wow.
Because you have much more thermal mass in there.
Yeah.
A lot more shelves. A lot more better insulation in the walls.
Right. Right.
And that's a classic expression of a quartz inversion cooling craft. Now, it is interesting that with each subsequent firing, you get more cristobalite crystals develop in your clay body, your ceramic body. And so these pieces become more subject to cracking, so we have to be attentive to the rate at which we heat up the kiln and cool down the kiln. You probably don't want to put a piece like this hanging over, on the bottom shelf right over the flame.
Right.
Have it higher in the kiln.
So loading the kiln, there's a lot to think about as you're loading where to.
Yeah, occasionally, because most of the time we don't have pieces of this size
Yeah.
in the kiln, but sometimes there are.
Yeah.
Like a cat.
Now, interesting, three-dimensional forms like that are actually more
Because
durable.
you're going vertical.
Well, it's a more compact form.
Okay.
You've got height, but if somebody's thrown a wheel-thrown piece that's 4 feet tall in the kiln, that can be problematic
Huh.
because you have enough difference in temperature from the hot
Top and
to the
top and bottom.
bottom and top.
Wow.
Okay, if you'll turn to page 4. How you doing? This is a lot of information again.
Yeah, it is. But that's okay. It's making sense to me now. Little pieces.
Bits and, okay.
Yeah.
So
Okay, I get
I'd
it.
like you to just simply read the description here of vitrification.
All these technical terms. Feldspathoids.
So when you use the word flux here, what is it specifically referring to?
Any fluxing agent promotes melting.
Okay.
I knew that. I found that out over the weekend.
Yeah, I see. I just gave a whole lecture on electric flux
Yeah,
last
that's a
night, and it's
different-
and it, yeah,
different.
and in that context, it means the penetration, something
Wow.
that penetrates.
Melting, penetrating, it could be a snow.
Well, it's not really the same thing. It's the idea of like this with how much of it goes
Oh, yeah,
through.
yeah.
If you think of a a screen, how much of a
Penetrate.
field
Yeah.
actually goes through it, as opposed to maybe sliding along the surface. So, yeah, it's a couple of times I've discovered that terms that I think I know are used in a very different context in here. And, well, and this is actually one of the first things I tell my students in physics classes is that we will use terminology that you think you know what it means, but it has a very specific meaning in physics.
Yeah.
And,
Has its own language.
Work is one of them.
Yes, yes, isn't that so?
Yeah.
So there's the technical description of what's taking place during vitrification. And it's important to know that two other things occur.
Hold on a minute, I can't hear you.
Trying to listen, trying to
You'll have to
learn.
get you a microphone.
Jesus, yeah.
And put headphones on each of you and we'll have a private thing. So, during vitrification, the clay body, now a ceramic body, in this process shrinks. And it shrinks by about the same amount as it shrank from wet clay to dry clay. Pretty shocking.
Yeah.
That's about 6.5 for low fire white, 7.5% for high fire bodies. So total shrinkage of a high fire piece is going to be 14 or 15%. A low fire white piece is going to be 6.5 period, just the wet to dry.
Better make that cup a little bit larger.
You know, it takes me, my brain as I'm making my things, you know, I make it to the size I think I like, and I keep forgetting that, and it gets, when I was doing the empty bowls, told myself make bigger bowls, so I could shrink, so it could shrink to a normal size bowl. But it takes a while for the brain to connect to that.
Yes, it does.
To me, anyway.
Yeah, and just about everything else in life. So it's all about the journey and experience.
Wow.
But here's the technical
impressive.
stuff that we'll be dealing with the rest of the semester in these terms. Now, not only does it shrink, but while it shrinks, it's soft.
Because of the plasticity?
No, not in this case. It's the
Just
material has
malleable.
become malleable or plastic yet again
Okay.
as it shrinks. So if I have,
It's just, when it's in that state, it's actually transformable if you could touch it, if you could exert pressure on it.
So bisque firing basically just stabilizes it at one point.
right, and in earthenware, it's also the end point. Right? The highest temperature we go to with earthenware.
Yeah.
But I've got this bowl in the kiln, and Mike is rushed. This is a learning institution. And the shelves sometimes get in pretty bad shape because of all the drips and various problems with less experienced folks using it. And this piece is now up there around cone 7, cone 8. It's going through vitrification. It's somewhat soft. And it's trying to pull inward here and shrink. And the feet are catching on rough spots on the shelf. And what went in is a beautiful round ball comes out oval shaped. In most cases, that's not too much of a problem. Here's a problem.
It happens a lot with porcelain.
This is not an
For me,
exact
anyway.
science at all.
I'm fond of adding things to my work. Various
Yes.
kinds of handle and design additions.
Wine bottles.
So I have made what I expect to be is a spectacular tureen. And it's got these handles to dream about in the middle of the night.
This is going.
And in the process of the firing, the weight of these spectacular sculptural elements is pulling downward on the form. And so what started as a form like this comes out of the kiln as a form like this.
Because of the weight of those things.
Right.
Wow.
The folks who are in Saunders' wheel class periodically are assigned to make lidded containers,
Yeah.
but some folks don't like to have the rim left raw. And so they want glaze over the rim.
Yeah.
So they fire the lid over here sitting on the kiln shelf. And the lid gets distorted as it shrinks. And possibly the opening, and they try to put the lid in at the end of the process, and it doesn't fit into the opening that's there after the firing. Especially if they've followed Bob's great love of designer elements attached to the side of his pieces.
So,
So if I fire with a lid, I'm going to fire with the lid in place
okay.
with all of its
Stuff.
stuff.
On top of
So you should fire with the lids on
If you want them to fit.
if you want, because okay, so all of mine, I fired separately and they all fit, but the one that I fired, the teapot with the lid on, it blew. The whole lid blew, the center of the lid blew. Yeah, it was really good. Yeah.
That's interesting. I don't
Was it
know.
not releasing
Yeah, now
enough
the
pressure
people who do
inside?
this and fire them separately also have lids that go clang, clang, clang.
Yeah,
I don't have that problem either. My lids fit just
there'll be a time though.
I'll
So
study.
Yeah, I'm
Yeah.
sure there'll be a time.
Beginner's luck.
Okay, so there are issues that we have to deal with that are the result of the changes that happen in the kiln.
Wow.
And until you make really complicated forms, it's not too much of a problem. But it's part of the reason why you don't see much sculpture in the high fire kiln, because
Yeah.
these arms, when they get soft and vitrify, can easily end up in a different place.
Andy touched on that in the summer, that was actually one of the benefits of low fire clay, was that you had less of that at the
Yep.
low fire.
Yeah, this low fire clay, if you get it dry, you get it fired. You're set, as long as you don't blow it up. Page 5 simply indicates the various temperatures that we fire to in the studio. For all of our white clay bodies, low fire white, porcelain, B-mix, and WS10, we bisque fire at cone 04. For our brown clay bodies, we bisque fire at 06 or 08.
And the reason being?
Good question.
So that way you have to have a formal.
So you make something real thin, you know, and you put these big old beautiful things like.
Or the same thing with a coffee mug. You throw a thin mug, the minute you put that ample on.
I told you that we had a glaze that didn't exist anywhere else in the world.
Yeah.
That's it.
Wow.
Foil
Yeah.
machine.
Yeah, it's very pretty. I think I have some pieces that Sue Southern did.
That's nice and smooth.
What's the name of that?
Kuyamashino,
Kuyama.
like the city of Kuyama.
That's pretty.
Here is a piece of Amador that
Right.
was bisque fired to cone 06. Here is a piece of Amador that was bisque fired to cone 04. Are you feeling adventurous?
I did it at home already several times. I wondered why there was something different.
Okay, I would like you to first lick this one, and then lick this one.
One's drier than the other. Dry. This is real dry. This is nice. I like this better.
What's the difference?
Oh, this dried nice. This dried nice. This one did not. It is not dried.
So what she's describing is the behavior of mucus. Pardon?
I want to try that. What's the deal here? Oh, this one's, I don't know, it seems cooler or damper, or is that what you were getting at?
But look at when you're drying it. If you look at the
Oh.
one's drying very
Oh,
quickly.
yeah. Oh, I see what you're saying. Yeah, this one dried much faster than this one did.
That's 06, the lighter
So it
colored one.
closed it up more.
So what's happening, closed up is a good description,
Yeah.
is the iron that makes this body dark at cone 04 has begun to cause an fluxing action, vitrification of this body, and it's no longer as porous.
Is that in
We-
Long Beach clay too?
And that's at 04?
Yeah, which is
This is-
higher temperature than
This is a higher temperature
Yes.
than 06.
Right.
And so
Right.
we've lost a good deal of our porosity and
Yeah.
therefore absorption.
Yeah.
So when I take and glaze these pieces,
Yeah.
I'm going to dip them into a bucket
Right.
of water
And this one's
with
gonna
ground up
abs-
rocks. And the water's going to migrate into that porous bisqueware
Nicely.
and leave a layer of glaze. This one, as you took note of, is not as porous, and therefore when we
It'll
dip
take a long
it,
time to dry.
it'll take a long time to dry, and it may not even absorb
not
enough
work.
water to get a good, decent coating of
Right.
glaze material.
Right.
Wow, okay.
Okay,
Got it.
interesting.
So I only wanted to run one kiln load, and I wanted to fire all my tiles at the same time. And so I fired everything at 06. What's that do to my B-Mix and my WS10?
For your test tiles, probably not much.
Okay.
But as you make larger work, 04 makes the whiteware stronger.
Okay.
Okay.
But it makes the redware too strong. I mean, or too condensed.
Too dense.
Yeah.
Correct.
Okay.
And Long Beach clay would be like the Amador? Okay.
Amador's from Aardvark.
Sorry,
Yeah.
But I horse-haired them. I didn't glaze them. So that was the difference.
Cone 018 is where we use the metallic overglazes.
That's so cool.
You paint them on, fire them. They take on the character of the surface to which they are applied. If you put them on a matte glaze, it'll look like gold spray paint. If you put them on a gloss glaze, this is what you get. If you get them on bare clay, the metallic material is absorbed into the clay, and you can see you've got that dark purple there where it overlapped, and
Wow.
you'll get no gold at all. Given the expense of the material, particularly in the run-up on gold prices, you really do want to use that carefully, but it's spectacular.
So you use that on a piece that has already been glazed.
Already been fired and glazed, yes.
Already been fired and glazed.
Yeah. So part of the ceramic process very often involves stepping down or firing down. So you start at the highest temperature, and you can add something to the lower temperature, and add something at the lower temperature, and
That's
so
after
on.
you've done the cone 10, then you can add a new, okay.
And there's only one page left, I believe, in our handouts that we haven't looked at. It's entitled Temperature Range in Relation to Kiln Color.
So
Oh,
that's
that was the one where you were saying that you could see what color it is by,
okay.
or where the temperature was.
Doesn't
how
have a
far it had
page
been done.
number. Okay.
Wow.
Here it lists, no, these colors are a reflection of incandescent. And so this says the lowest visible red is at 885 Fahrenheit. I've never been in a perfect environment where the background colors were so dark that I could detect that. So it's usually around 1,000 degrees when I notice the incandescent.